let's look at the forward algorithm for hidden Markov models. Our goal is scoring. So we are given a sequence of symbols V, which is V1, V2 until Vt. So we have uppercase T time steps. And our goal is to find the probability of V. Now, the simple approach to do so would be to find P of V as this summation. So for every possible state sequence S of length T, we find P of S, and we find P of V given S, and this summation over all sequences will give us P of V. So what we need to do is we need to find for each possible state sequence S, each possible state sequence, we need to find probability of occurrence of that state sequence and probability of generating the given output sequence V from that state sequence. This is the problem of scoring. So our goal is to find the probability P of S given S first. So the first state of this state sequence is S1, and the probability of S1 is pi S1. Pi is the initial probability. The probability of S1 and S2 is pi S1 times the transition probability from S1 to S2, which is PS1 S2. The state sequence S1, S2, S3 has a probability pi S1 times pi S1 S2 times the transition probability from S2 to S3, which is PS2 S3. And so we continue until the last state S of t, and the probability of the last state being generated is Pst minus 1 St. Therefore, the probability of P of S given any state sequence S is pi S1 times P S1 S2 times PS2 S3 all the way up to times P St minus 1 St. Now the next goal is to find PV given S. How do we do that? So we have the state sequence, and now we are going to find probabilities of the output sequence V. Probability of V1 being generated from S1 is simply the corresponding emission probability QS1 V1. The probability of V2 being generated from state S2 at time 2 is the corresponding emission probability, which is QS2 V2. Likewise, probability of V3 is QS3 V3, and so on, until the time step uppercase T, the emission probability is QST, VT. And so we multiply all of them together. That gives us P of the entire output sequence V given state sequence S. We have already computed probability of the state sequence. So PV given S is given by this product QS1, V1, QS2, V2, QS3, V3, all the way to QST, VT. And P of S was initial probability pi S1 times transition probabilities PS1 to S2, PS2 to S3, all the way to P St minus 1 to St. Now we take the product of both, we multiply them together, we get the desired probability. So this PV given S times PS is pi S1 QS1 V1, then pi S1 S2, PS1 S2 times QS2 V2 all the way to PST minus 1 ST QST VT. So PV is the summation of all possible such S's, state sequences, of PV given that state sequence times PS. Problem. Now each term here requires one multiplication. Each factor actually requires one multiplication of a P with a Q. And the total number of state sequences is of length t is n to the power of t. This is the total number of possible state sequences S. Therefore, the total number of multiplications is order t n to the power of t. And this is computationally impossible when t is of a reasonable size, or n, the number of states, is of a reasonable size. Therefore, we require a different algorithm to find probability of V. That's where we have the forward algorithm and the backward algorithm. Forward algorithm. Forward algorithm, we'll first define the forward variable alpha. Alpha t comma I, where t is a time step and I is an index of a state, is equal to the probability of V1 through Vt comma St equals Si. In other words, alpha ti is the probability of the output sequence being generated up to Vt, the given time step, and the current state at time t being equal to Si. And of course, the time step can be between 1 and t. So here's how we can visualize the forward variable alpha ti. It's the probability of the outputs V1 up to Vt, the current time step t, and St, the current state at time t. And we will now derive from alpha ti an expression for alpha t plus 1j, which is the probability of, by definition, output sequence until Vt plus 1 now, because we have an index t plus 1, and the time step t plus 1 state St plus 1 should be equal to Sj, because the index is j in the argument. So now let's proceed to find alpha t plus 1j in terms of alpha ti. Now suppose at time step t we are in state S1 and we have accounted for the output sequence V1 through Vt. So that probability is equal to alpha t1. So we are in state 1. Then the probability of transitioning from the state 1 to state j in the next time step is p1j. And the probability of outputting Vt plus 1 is qj Vt plus 1. So the whole probability is this product, alpha t1 p1j qj vt plus 1. And that's visually given by shown in these two plots, with st being equal to s1. So here's what we have. We are given alpha t1, the probability of the output sequence until time vt, and the state at time t being s1, and so the probability of the sequence of outputs until vt plus 1 and st equals s1, and transitioning from s1 to st plus 1 equals sj is given by this alpha t1 p1j qvt plus 1. How is that? Because probability of v1 through vt is already accounted for by alpha t1. Probability of st equals s1 is also accounted for by alpha t1. And probability of st plus 1 equals sj, this transition probability is due to this factor p1j, and output emission being vt plus 1 is this factor qvt plus 1. Generalizing, suppose at time t we are in state si, and the probability of the output sequence being v1 through vt, the probability of that is alpha ti. And to that we can multiply pij to account for state st plus 1 being sj, and qjvt plus 1 to account for the next output symbol being vt plus 1. So alpha ti is defined, and probability of v1 through vt plus 1, st equals si, and st plus 1 equals sj. This joint probability is given by this expression. The alpha ti accounts for the output sequence v1 through vt and the state st being equal to si, and the probability of st plus 1 being sj is accounted for by this p1j transition probability, and the probability of the output being vt plus 1 is accounted for by qvt plus 1. So we have alpha ti, and that's by definition the probability of the sequence of outputs v1 through vt and st being si. And we saw that with this probability of the output sequence until vt plus 1 and st equals s1 and st plus 1 equals sj is given by this expression here. This is the probability of the output sequence until vt plus 1, probability at time step t being s1 and jumping from s1 in the next time step to j, state sj. And in general, it is for the time step t, the state being si, and then jumping to state sj in the next time step is given by this expression here, and until time step, until sn, st equals sn. And so alpha t plus 1j is equal to this probability of v until time step t plus 1 and at time step t plus 1 st plus 1 being equal to sj. What we have to do is, we see here we have computed these probabilities here, and here the additional requirement is ST is S1 in the first one, ST equals SI in the ith one, and ST equals SN. So if we add up all of these, then we eliminate the condition for ST. Therefore, alpha t plus 1j is simply equal to the summation of all of these probabilities, which is summation alpha ti pij times qj vt plus 1. So the transition could have been from any state I equals 1 through n, this transition, st to st plus 1. And we are summing it all up to get summation alpha ti pij. So this is the probability of being in state Sj at time t plus 1, regardless of what was at time t. And this is the output probability at time t plus 1. So here are the components of the forward algorithm. By definition, alpha ti is probability of the output sequence v1 through vt and the time step at t being si. Now, at the initial time step 1, this is the probability. By definition, alpha 1I is probability of v1, comma s1 being equal to si, and that's easy to compute. Probability of s1 being si is simply pi I, the initial probability, and probability of v1 being generated from si is qi, comma v1. We already saw this expression for qt plus 1j alpha t plus 1j from alpha ti. And now let's plug in the value uppercase T in alpha here. So that's the probability of the entire output sequence until the uppercase T and terminating at time step uppercase T at state Si. And that's P V comma Si. So this is the probability of V1 through V uppercase T, and that's the entire vector V, and probability of St equals Si is probability of Si. And so to find probability of V, all we have to do is sum over all possible Si's. That is summation of I equals 1 through n of alpha Ti equals probability of V. That's our goal to find out. So now let's proceed with the forward algorithm. We initialize alpha 1 i's for each value of I, each state I. We initialize alpha 1i to be equal to pi I times qi v1. And then let's say we proceed from alpha 1i, we proceed forward, and at time step t, we have the values of alpha ti. Now, how to compute alpha t plus 1j from the alpha ti's is using that summation that we already saw. So this is given by this recursive equation. Alpha t plus 1j will be equal to summation alpha ti pij times qj vj comma t plus 1. This is alpha ti. For each I, we compute alpha ti times transitioning from state I to j, which is pij, and then we multiply that with the output probability qj vt plus 1. And we proceed until the last time step t. So this is the forward algorithm. We initialize for I equals 1 through n, alpha 1i equals pi I qi v1. And then we move forward recursively. So at any time step t, we have the value of alpha t i's for all i's. And then how do we compute alpha t plus 1j? Using this expression. For each j, each new state j at t plus 1, alpha t plus 1j, we use this expression. And then at the end, once the alpha ti's have been computed for uppercase T, we find the probability of V, the entire output sequence, as the summation of all those alphas at uppercase T time step. So what's the algorithm complexity? The for loop will concentrate on this main algorithm. The for loop iterates t times, and the inner for loop here iterates n times, number of states. And this summation is also carried out n times. So the complexity of the forward algorithm is order n squared t. The end.